Installing an emergency generator to serve two separate freestanding buildings presents unique grounding and bonding challenges. Each building will have its own grounding electrode system, and connecting them together can create ground loops. The generator's neutral must be grounded at the generator, but it cannot be bonded to the grounding electrode system of both buildings without creating a parallel path for ground current. Balancing the electrical load between the two buildings and the generator's capacity can be complex. If one building loses power, the generator must be manually switched over to supply that building, which could cause delays and potential safety risks. If a ground fault occurs in one building, it may not be detected by the generator's protection devices, posing a risk of electrical shock. Article 250.94 A1 requires grounding electrode systems for each building. Article 250.24 B prohibits connecting grounding electrodes together where separate services are involved. Section 5.26 requires the generator's neutral to be grounded at the generator. Section 5.28 requires the generator's neutral to be bonded to the service disconnecting means of the equipment being supplied. It is not recommended to install an emergency generator to serve two separate freestanding buildings with separate services. The potential grounding, bonding, operational, and safety issues outweigh the benefits. Consider the following alternatives. Firstly, install a separate emergency generator for each building. Secondly, install an automatic transfer switch in each building to automatically switch between utility power and an on-site generator. Thirdly, establish a microgrid with distributed generation sources, energy storage, and load management systems to ensure redundancy and resilience. When installing an emergency generator, several key factors should be considered to ensure proper operation and safety. These considerations encompass grounding and bonding practices, compliance with relevant codes and standards, and the selection of appropriate equipment and configurations. Grounding and bonding are crucial for creating a safe and effective electrical system. The primary purpose of grounding is to provide a low impedance path for fault currents to return to the source, thereby facilitating the operation of overcurrent protection devices like circuit breakers or fuses. Bonding, on the other hand, involves connecting all non-current carrying metallic parts of the electrical system to create an equipotential plane, minimizing voltage differences and reducing the risk of electric shock. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding and bonding in Article 250. It outlines the requirements for grounding electrode systems, which typically include ground rods, ground rings, or connections to metal water pipes. The NEC also specifies the methods for bonding various components, such as metal conduits, enclosures, and equipment grounding conductors. In the context of an emergency generator serving multiple buildings, special attention must be paid to the grounding and bonding arrangements at each building. Each building should have its own independent grounding electrode system, as required by the NEC. Connecting the grounding electrode systems of multiple buildings together can create ground loops, which can lead to circulating currents and potential safety hazards. The generator's neutral point must be grounded at the generator itself. This grounding connection provides a reference point for the generator's voltage and helps to stabilize the system during normal operation and fault conditions. However, the generator's neutral should not be directly bonded to the grounding electrode systems of both buildings. Doing so would create a parallel path for ground current, which can lead to nuisance stripping of overcurrent protection devices and other problems. To avoid these issues, it is recommended to use separate grounding and bonding systems for each building, with the generator's neutral grounded only at the generator location. The NEC also addresses the use of separately derived systems, which are electrical systems that receive power from a source other than the utility grid. Emergency generators are typically considered separately derived systems, and they must comply with specific grounding and bonding requirements. Article 250.30 of the NEC outlines these requirements, including the need for a grounding electrode conductor to connect the generator's neutral to a grounding electrode system. The size of the grounding electrode conductor is determined by the size of the generator's conductors, as specified in Table 250.66 of the NEC. In addition to grounding and bonding, compliance with other relevant codes and standards is essential for a safe and reliable emergency generator installation. NFPA 110, the standard for emergency and standby power systems, provides detailed requirements for the installation, testing, and maintenance of emergency generators. NFPA 110 covers a wide range of topics, including generator sizing, fuel supply, exhaust systems, and control systems. It also includes specific requirements for the transfer of power between the utility grid and the emergency generator. The automatic transfer switch, or ATS, is a critical component of an emergency generator system. The ATS automatically switches the load from the utility power to the generator power when a power outage occurs. It also switches the load back to the utility power when the power is restored. The ATS must be properly sized and rated for the intended application. It should also be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories, or UL. When selecting an emergency generator, it is important to consider the specific needs of the application. The generator must be sized to meet the total load requirements of the building or facility that it will serve. The load calculation should include all essential loads, such as lighting, heating, ventilation, and air conditioning, as well as any critical equipment that must remain operational during a power outage. The generator's fuel supply must also be adequate to meet the expected runtime requirements. The fuel supply should be sized to provide enough fuel for the generator to operate continuously for the duration of the longest expected power outage. The generator's exhaust system must be properly designed and installed to prevent the buildup of dangerous exhaust gases. The exhaust system should be vented to the outside of the building in accordance with all applicable codes and regulations. The generator's control system should be designed to provide reliable and automatic operation. The control system should include features such as automatic start and stop, automatic voltage regulation, and automatic load sharing. The control system should also provide alarms and notifications in the event of a generator malfunction. Regular testing and maintenance are essential for ensuring the reliable operation of an emergency generator. The generator should be tested periodically and allowed to verify its ability to meet the load requirements. The generator's engine should be inspected and serviced regularly in accordance with the manufacturer's recommendations. The fuel supply should be checked periodically to ensure that it is adequate and that the fuel is fresh. The exhaust system should be inspected regularly for leaks and corrosion. The control system should be tested regularly to verify its proper operation. In addition to the above considerations, there are several other factors that should be taken into account when installing an emergency generator. These factors include the location of the generator, the noise level of the generator, and the availability of maintenance services. The generator should be located in a well-ventilated area that is protected from the elements. The generator should be installed on a concrete pad or other suitable foundation to minimize vibration and noise. The noise level of the generator should be considered, especially if the generator is located near residential areas. Noise reduction measures may be necessary to comply with local noise ordinances. It is important to choose a generator supplier that offers reliable maintenance services. The supplier should have a team of qualified technicians who can provide regular maintenance and repairs. The supplier should also have a stock of spare parts to minimize downtime in the event of a generator failure. In summary, installing an emergency generator requires careful planning and attention to detail. Grounding and bonding are critical for creating a safe and effective electrical system. Compliance with relevant codes and standards is essential for ensuring the reliable operation of the generator. Regular testing and maintenance are necessary to verify the generator's ability to meet the load requirements. By following these guidelines, you can ensure that your emergency generator will provide reliable power when you need it most. Furthermore, when considering emergency generators for multiple buildings, several advanced concepts and technologies can enhance the system's performance, reliability, and efficiency. These include microgrids, advanced transfer switches, and remote monitoring systems. A microgrid is a localized energy grid that can operate independently from the main utility grid. Microgrids typically include distributed generation sources, such as solar panels, wind turbines, and emergency generators, as well as energy storage systems, such as batteries. Microgrids can provide a number of benefits, including increased resilience, reduced energy costs, and improved environmental performance. In the context of emergency power, a microgrid can ensure that critical loads remain powered even during extended utility outages. The microgrid can automatically switch to island mode, disconnecting from the main grid and operating independently using its own generation and storage resources. This can be particularly beneficial for facilities that require uninterrupted power, such as hospitals, data centers, and emergency response centers. Advanced transfer switches offer enhanced features and capabilities compared to traditional transfer switches. These features can include seamless transfer, soft loading, and advanced monitoring and control. Seamless transfer switches minimize the interruption of power during the transfer process. This is particularly important for sensitive electronic equipment that can be damaged or disrupted by even brief power outages. Soft loading allows the generator to gradually pick up the load, reducing stress on the generator and minimizing voltage fluctuations. This can improve the generator's performance and extend its lifespan. Advanced monitoring and control features provide real-time information about the status of the generator, the transfer switch, and the load. This information can be used to optimize the system's performance and to identify and resolve potential problems before they cause a power outage. Remote monitoring systems allow you to monitor the performance of your emergency generator from anywhere in the world. These systems typically use a web-based interface or a mobile app to provide real-time data about the generator's status, fuel level, and operating parameters. Remote monitoring systems can also send alerts and notifications in the event of a generator malfunction or a power outage. This allows you to respond quickly to potential problems and minimize downtime. In addition to these advanced concepts and technologies, there are several best practices that can help to ensure the reliable operation of your emergency generator. These include regular inspections, preventive maintenance, and load testing. Regular inspections should be performed to identify any potential problems with the generator, such as leaks, corrosion, or loose connections. Preventive maintenance should be performed on a regular basis to keep the generator in good working condition. This can include changing the oil, replacing the filters, and inspecting the engine. Load testing should be performed periodically to verify the generator's ability to meet the load requirements. This can involve connecting the generator to a load bank and measuring its voltage, current, and frequency. By following these best practices, you can help to ensure that your emergency generator will provide reliable power when you need it most. Furthermore, consider the application of load shedding and prioritization strategies. Load shedding involves selectively disconnecting non-critical loads during a power outage to reduce the demand on the generator. This can help to extend the generator's runtime and to ensure that critical loads remain powered. Load prioritization involves identifying the most critical loads and ensuring that they are powered first during a power outage. This can be achieved through the use of automatic transfer switches or manual switching devices. When implementing load shedding and prioritization strategies, it is important to carefully consider the needs of the facility and to develop a plan that meets those needs. The plant should identify the critical loads, the non-critical loads, and the order in which they should be disconnected or powered on. In addition to the technical aspects of emergency generator installation, it is also important to consider the regulatory requirements. Emergency generators are subject to a variety of regulations, including environmental regulations, building codes, and fire codes. Environmental regulations may require the generator to meet certain emission standards or to obtain a permit to operate. Building codes may require the generator to be installed in a specific location or to meet certain structural requirements. Fire codes may require the generator to be equipped with a fire suppression system. It is important to consult with local authorities to determine the specific regulatory requirements that apply to your emergency generator installation. Finally, it is important to choose a qualified and experienced contractor to install your emergency generator. A qualified contractor will have the knowledge and expertise to ensure that the generator is installed correctly and that it meets all applicable codes and regulations. The contractor should also be able to provide ongoing maintenance and support for the generator. When choosing a contractor, it is important to ask for references and to check their qualifications and experience. You should also make sure that the contractor is licensed and insured. By following these guidelines, you can ensure that your emergency generator is installed correctly and that it will provide reliable power when you need it most. These strategies and considerations will greatly enhance the safety, reliability, and efficiency of the emergency power system, particularly when serving multiple buildings.